I'm going to jump into one of the essential problems of the subject of color theory, and that is this beginning definition of what is color. Where does it live? Where does it reside? How do we activate it? How can we manipulate it? Generally, we think that color lives in things, that there is redness in this red plastic calculator. But you also know that you could not see that redness if it were not activated by light. So that should lead you to realize, I hope, that the redness in the calculator has to be activated by light. Therefore, the redness is largely existing in the light itself and not in the calculator. Light from the sun we consider to be white light, and that is our reference for light, as white light from the sun. But we have learned about 300 years ago that white light from the sun is actually made of all colors. If we take out the red component of that white light, which is one of the primaries, the three primaries of light, we no longer have any red that we can see. We need the red light to see red in the calculator. So the redness does not live in the calculator. The redness lives in the light. That light, which we consider to be white, is made of this entirety of colors. You might recognize these colors in this sequence of colors from the rainbow. We call this the spectrum. And the spectrum, when combined, gives you white light. But that is only part of what we get from the sun. The electromagnetic spectrum, which is all of the energy we get from the sun, is largely unavailable to human sensors. We are not aware of AM radio waves bouncing off of our body. We're not aware of infrared. It's there all the time. What we're aware of is light and to some extent heat, which is a minimal part of what the sun actually hits us with every day. This is an octave. And an octave is the measurement, in this case, between the crests of two waves. So we're considering this to be vibrational energy, and this is one vibration. A doubling of that octave happens, and we go into another octave. A new octave is now twice as large as the last one. This happens 60 to 70 times in the electromagnetic spectrum. But what we see is just this one octave that we call visible light. We think that's sunlight. And it actually, when you look at it much more closely, it is no longer seen as white light. It is now seen as a wide variety of colors. So that would lead us to believe that, well, okay, color is not in the object. I see your point, but is it light? And not necessarily. That's not the whole story. Because we need a human being, an observer, to recognize it as color. When light comes into our eye, it goes through the optic nerve to the back of the brain, and we start processing those electrical signals from the eye that eventually are going to be turned into color. This is the primary visual cortex. But this, by the way, is where the eyes are in the front of the brain. So they go all the way, the signal goes all the way back here. And the primary visual cortex is interested in value, in dark and lightness. It is not interested in color, and does not do anything with color yet. It gives us orientation information. It tells us where edges are, where contours are, where detail is, and whether those edges go up and down or left and right or diagonal. From there, that information then is passed to V4 and V5 and other parts of the brain, where we then add color associations or color information to it, and then it is brought to the front of the brain, the frontal lobes, where we add memories and other associations with it. And when we're finished that entire process, which takes a millisecond, we say, oh, red plastic Hello Kitty calculator. We have tried to understand color systems. We have tried to categorize how these colors work together so that we can manage them better for thousands of years. And Aristotle was probably the first person to actually write this down. So over 2,000 years ago, Aristotle came up with this system that you're looking at right now, an organization of color based purely on relative darkness and lightness. White is on top, black is on bottom right after dark gray, and red, magenta, and green are right in the middle. And these are not colors that really have much to do with each other, as you might already know. Well, they don't have anything to do with each other as hues, but they are all similar in value. And that's what was most important to Aristotle and to most of European history for the next 2,000 years. Isaac Newton, 2,000 years after Aristotle, allowed a white beam of light to go through a prism. He's not the first person to do this, but he saw that there was a spectrum, a rainbow, that came out of it. And he suspected that white light is made of this. Other people at that time thought that the spectrum was added to the white light by the prism, that the prism was a magic element. But he thought, no, it's not. I think that what I'm doing is being able to analyze and break apart and deconstruct white light. So to prove it, he took a second prism, put it in that spectrum, and saw a white beam of light come out of that. It collapsed the light back again into white, and he proved that white light is actually not white. Whiteness is made of many, many different colors. So the next thing he did, he took that linear spectrum, that sequential gradation of colors, and he connected the two ends, the dark red end and the dark blue-violet end. And once he did that, he needed another color to fill them up. This is almost a transitional connecting link that he had to add because it's not in the spectrum. This magenta or purple color is really not in the spectrum. What he ended up with is what we now call an additive color wheel. Now, he was trying to understand the nature of light. He was not trying to help artists. So he didn't do anything with this. And it took quite a while before somebody else realized, you know, maybe artists could actually use this. It took a couple generations before we realized that. So you're looking at an additive color wheel right now. But that is sort of a mask over how colors can group and overlap and combine. So if I take this mask away, you can see that this additive color wheel, when colors go towards the center, add one color to another color, and each one adds more light, finally making white light. On the edges, if we went further than this, we would go into the darkness of space. We'd have a void. That's hard for us to manage. We are much more comfortable with this in terms of circles. So what you are looking at now is the primaries of additive light: green, red, orange, and blue, violet. And when they overlap, we get the secondaries of additive light: yellow, magenta, and cyan. And when they all overlap, we get white light. Okay, these again are the primaries. The idea of primaries is an unusual idea. It does not come from the world of art. It came from the world of business. And it was not part of how people organized color until the 17th century, when a man who dyed wigs for aristocrats figured out that he could use only a few colors to make all the colors he needed. And this is the first time somebody wrote that down. But we didn't know what those few colors are. That was just simply the concept of primaries. Primaries are the basic colors used that other colors can be mixed from. You cannot make a primary. You have to start with a primary. But from primaries, you can mix many other colors. Light uses these three primaries. Notice they're not red, yellow, blue, because that's not light. That's reflected light. The secondaries of light, which I just pointed out a minute ago, are yellow, magenta, and cyan. And these are additive colors, but subtractive color wheels. A subtractive way of using color, used by printers, uses these three colors, which are secondaries in additive color, as primaries of printing. And we know this now because in the last 100 years or so, we have discovered that this probably gives us the widest range of colors you can mix from. But they're awfully harsh for a painting. So painters tend to use these almost sort of psychological primaries of red, yellow, blue. This now is the subtractive color wheel. If the additive color wheel adds color together and makes more light, the subtractive color wheel does the opposite. It prevents light from being reflected off an object and essentially gives you darkness. When you mix these together, you create darkness. And as they expand outward from that dark center, they just simply dissipate into whiteness in general. And we try to manage this, again, in terms of these circles. Now, we could have used yellow, red, and blue, but we're not. This is yellow, magenta, and cyan, because as I said before, these probably give us the widest range of mixing. And when they overlap, they give us the primaries of light, but when all of these overlap, they give us black. Art schools arrange these colors in this form. This is a standard art school color wheel in 12 steps. It begins as subtractively with yellow, and then a primary red and a primary blue. The secondaries, violet, orange, and green, are then part of it, and we fill all the missing spaces in with what we call tertiaries, which I'll show you in a minute. Now, this is a subtractive color wheel, and there's one thing important about this as an arrangement of colors, and that is yellow, green, and red, violet create an axis. And everything in the color wheel we're looking at right now, everything on the left side of this axis is what we call a warm color. Everything on the right-hand side is what we call a cool color. Well, that's for a subtractive color wheel. This is an additive color wheel. And you'll notice that very little of it is warm. There's like a lot more green, there's a lot more blue in an additive color wheel, which doesn't make sense because this is how the eye works. The eye works based on these three primaries of light: red, orange, blue, violet, and green. How can that be? Because we see a lot of reds and we respond to reds very strongly. The answer is because the eye has so many red cones and they're all directly connected to the brain. So that is the compensation factor for the nature of how light works, is that we tend to be more sensitive to the warm parts and we balance it out that way. Many color wheels exist. This is called the Munsell color wheel. It is based on an additive color wheel. Essentially, it is an additive color wheel, but it is used for reflective art, paints. Albert Munsell was the man who designed this. It was about 100 years ago, and he was frustrated that we couldn't rely on regular language-based names for colors, so he wanted a more exacting system. He has 5 primaries in his color wheel, by the way, because he wanted 10 basic colors. This is yet another color system, which is called the Natural Color System and sometimes called NCS. It is officially used by some Scandinavian countries and some other parts of the world, and it's based on the ideas of a man named Ewald Hering, who lived in the 1870s. And he thought the color works the way it does because of 3 pairs of opposites. These pairs of opposites are white and black, or dark and light, green and red, and yellow and blue, which makes green a primary color and also makes darkness and lightness have a different relationship to the colors than in most other color wheels. A color wheel based on this way of thinking actually emphasizes yellow and green a bit. But this is a psychological color wheel. This does not help you manipulate light and does not help you manipulate paint, but it does help you make well-tuned impressions on a brain. We are back to our art school color wheel, our 12-step subtractive color wheel, which is the one most people learn when they take an art class or a color theory class. This century, in the 20th century, we have settled on this being the way to teach color. It is not a wrong way, but it is a limiting way, and I do want to let you know that there are other ways of thinking about this too. The primaries of this color wheel, in kindergarten terms almost, are yellow, blue, and red. And we have been told that these are primaries and you can mix all colors from them, which is, as you have learned by now in your life, blatantly untrue, barely close to being true. But these are anchor points for our views of the world, for our sense of perception. In between those primary colors, those anchor points on the subtractive wheel, we have secondary colors. There are people who feel that these are weaker colors, which I think is something you learn in your culture rather than something that we can prove as a physical fact. These secondaries appear to exist in between the primaries. So a green made of yellow and blue looks like it fits perfectly in between the yellow and blue. That is not a guarantee that mixing 50% yellow and 50% blue is going to give you a perfect green, though. All paints and all dyes all have individual properties that will probably get in the way of that idea. In between the primaries and secondaries, we have tertiaries. Tertiaries just means sort of third. And I want to recommend that when you refer to tertiaries, you use the primary color name first. So that would mean this is a blue-violet. It is not a violet-blue. This is a yellow-orange. It is not an orange-yellow.